Hello, and welcome back to Learning with Lee. In today's episode, we are going to continue to take a look at structs and linked lists. In particular, we are going to start off by taking a look at how we create a linked list. Because to be fair, if we wanted to, we could skip over all these functions, just really have a struct link, and then wherever we needed, say in intro.cpp, just start putting together one link after another link, and not really care about any of the other things that happen to be there. And what this, though, does is this ends up allowing us to make it a bit more reusable, so as we don't have to go through the same exact processes of creating, inserting, and deleting links in a list and tracking those things that we would otherwise have to do in case we were to not have these functions here. So, what we're looking at first is we're going to take a look at this new list function. And what new list does is the first thing it does is it allocates a linked list size piece of memory. So enough memory to fit an unsigned int and a link pointer. And what you're going to see a lot throughout here are these link pointers, as well as then down in here, list pointers. And these are related to these two lines up here, in which I'm using the typedef keyword to basically use a shorthand in place of this type. So everywhere where I would have list pointer, and you can see how many places that is here, not to mention all the places in here I would end up using that. Instead, I would end up having to use struct and then linked list and pointer. Or in the case of a link pointer, struct, then linked, then the pointer. And you can see over in here in the malloc, where I'm doing this, that's because structs are different than things such as an int or a float where it's just a single word. You actually have to include both struct and the name of the struct that you want when you are referring to it. So if I wanted to do this, I would have to do something such as struct linked list pointer, which I've shorthanded via typedef to list pointer. So that ends up making it a bit simpler, a bit cleaner, and a bit more concise for you to be able to read and use the software. So the first thing is that I'm doing this all on the heap, so we're going to change this up some in the future so as that we can use a bit more of the stack, but for now, what we're looking at happens to be we're going to create a list on the heap. We're going to check if it's null. If it's not null, we're going to initialize its variables. And this is a very important step whenever you're creating a new struct or a new object, as we'll get into later on, is that you want to guarantee that whatever happens to be within your list when you first create it is some known value. Because if for whatever reason it says my count is 20 when I have no items in here, then I might have aberrant or incorrect behavior later on in my program where I'm using it. Because it might say, oh, you have X number of items in there, when in fact we have 0 items. So that's very important. Same thing for initializing this to a null pointer, because otherwise we might be pointing to memory we don't have access to, which could cause our program to crash. So those are a couple major things there. You'll see that over in here I have a new link method, which, very similar to that one, ends up creating the memory on the heap. Then I end up using what I call reset, because I'm using this across multiple functions here, just as easier to have a single function for that rather than write it out in all 3 of those places, in which it just basically sets it so as that it ends up linking to itself. I could have it linked to null pointers, but this way is a bit safer and easier for it to deal with. So what we're looking at then is that so is that if we successfully malloced it, and reset also has this check to make certain that it's not null, then we also want to assign, and because we're storing an int in it, we want to assign that value to the item for storing it. So those are how we're going to be initially creating these objects. But then how are we going to actually insert, and this is really the next step, once you have your list, you need to be able to insert a link into that list, so a new item. So the first one is this insert method right up here. And what this does is it takes in an int item, creates a link for that item, and then first makes certain that we successfully actually created that link. And if it is, it either puts it in the first spot because it's the first item that's there. It allows you to automatically set it to the last element in case you give it a negative position, which is its default values, that it goes to the last element in the list. And then it also has the option of, in case, say, you gave it a position of 1,000,000 and you only have 100 items in your list, it automatically just puts it at the end. And otherwise, it'll have to iterate through the list, in case you remember how I had the whole graphics in the previous one of it jumping from one memory spot to another. So it needs to iterate over that list, find whatever item is supposed to go after it, and inserts it. And this one here exists in this file. And part of what I did here was I split up these functions into two files based on which ones are related to link and which ones are related to list. So it's a bit cleaner, a bit easier to understand. I could have even frankly further split it up if I had wanted to. But for now, this is good enough. So in this one, then all it does is it goes, okay, we need to update, and this is the major thing about linked lists. And this is the tricky stuff that you have to get used to dealing with when you look at linked lists and deal with their pointers, is that whenever I want to insert a new link into a list, I need to make certain that basically whatever the previous item in the list's next item points to this link's previous item is the correct thing that would be before it. And this link's next item points to the correct thing after it, as well as that thing that's after it now points to this item. So basically we end up having to update 4 different pointers. So within here, you can see here we're updating the previous item, as well as then we're updating the next item. And the major thing that I'm doing here that you'll notice is that I'm caching or temporarily storing the previous item in the list, because if I end up, say, updating what the next item in the list is that ends, well, next previous item to link, then all of a sudden my linked list won't end up working correctly. Let me quickly hop into Paint and I'll show you what I mean. So suppose that I have some different links in my chain, and I'm just going to call this one A and B, and then I want to insert link C into it. Right now, A has a pointer to B, and B has a pointer to A. What I need to do is I need to move this pointer from A to B to point to A to C, as well as then create one from C to A. But let's say that all that I currently have knowledge of in my insert algorithm is C and B. So, if, for example, I were to delete this one here and point B to C, I would have to iterate all the way around through the loop of my list until I reach here in order for me to find A again. So that's why I have to store A, because otherwise what's going to happen is that I'm going to lose some of these pointer information. Alternatively, I can just basically go, okay, let's go to A, basically use B to access A, update its one, update C's one, using that there, and then doing this. The whole reason why over here I assign previous to its own temporary link pointer is because of the fact that it's a bit cleaner than me having to go, okay, because the alternative, if I just were to comment this out, would be everywhere I have this, I would have to go, okay, this over and then do previous item, and so on and so forth. And it would end up being uglier, as well as also the way in which it would end up being compiling could be a bit less efficient. So as a result, it's a bit better to just basically go, I'm going to store A off to the side, so it's that even if I end up deleting this one here, I can still just go, let's still update A, and it won't have any complaints or problems. So that's what those do, and in the event that next is null, or for that matter, if next doesn't have, for whatever reason, a previous item, both of which are problems, then it will just basically have the link pointing to itself. And that's to avoid some of the issues of possibly having these null pointers. Frankly, there shouldn't ever be any, but because of the fact that we don't yet have, and this is one of the problems with structs, anywhere in my code that I have access to this namespace and am using link, I could just specify all of a sudden that next item equals null pointer. I don't have the ability to limit it so as that you can only access it through these functions. Because then, if I had that ability to limit it, I could guarantee that the next item in the link, as well as the previous item, were never null. At bare minimum, they would point to themselves. So that happens to be a minor thing to note about here and about structs also. So once we have it inserted, then let's say that we wanted to take one from one list. So let's just say I've got A going to B, and then C is now at the end of the list, just to go with a slightly different one. And let's say that I want to then take B out of this list and put it in a different list. And we'll just go with having D and E for now is the two that we care about where it would get inserted between. Well, the first thing that I would have to do is I would need to remove it from this list up here. And to do that, I need to make certain that I can update A to point to C and C to point to A. So basically, this needs to be sort of the new arc that we're dealing with in terms of how the pointers go. And the way in which you remove it from this, if I head on over here and head on down to this, is this remove links method. And what it does is it takes in a single link pointer. And that pointer is to the link you want to remove. So in this case here, it would point to B. If this were a singly linked list, I'd either have to point in a link to A, because otherwise B wouldn't know where A is without basically having to iterate over the entire list. Or, alternatively, I could pass in A and B, just to make it a bit cleaner, but by passing, if I were to pass in A, that would have B, just as that then it would be more confusing, because the element I would be passing in isn't the one I'd be removing, but rather the preceding element. So, what we then do with it is that we end up, and this is important also, we end up returning a link pointer. And the reason we return a link pointer is that, let's say that I, instead of removing B, removed A. If I did that, and in this case here, we just add in a whole bunch more little boxes around here, and you can think of this sort of like a bracelet in which, say, it's a string with a whole bunch of either little plastic beads on it or the like. You only need to have, in this case here for our linked list, a single pointer into here, and it points to a certain element in there. And in case I remove that element, I then need to update this pointer, because otherwise I'm going to have all of this just floating off in memory, and since this is on the heap, it's going to remain there until freed. It's just going to be floating there in memory and taking up space and possibly causing other problems. So what we need to do with it is that we really just need to be able to get the next element in that list, so we can just easily update our pointer to that next element. So that happens to be why we're returning it. Then down in here, we're doing this check just to make certain that link ends and all of these different items that are adjacent to our link aren't null. And that's a problem in that right now, we could actually guarantee that they wouldn't be null if we could guarantee that people would go through new link to create a brand new link pointer and a brand new link. Unfortunately, due to what we're dealing with right now and some of the way that C++ happens to be, right now somebody can just access link and assign next item and previous item to whatever they really want it to be, provided it's a link pointer, or something that can be cast into a link pointer. So it's a matter of, we have no guarantee that it's a valid value and that's not null in there, so we do need to do these checks. And then in here we just start storing the next item so that we can return it, and then assigning those two pointers that I talked about, basically going here and here. And those happen to be really the rest of it. And the final thing is that we're resetting the link, which I had already shown briefly earlier. And that's so as that if I add B to this new list, I don't want to be able to incidentally affect A or C. those are things that I don't want to end up having that ability to do. Or if somebody else is using it, I don't want them to, by accident or by deliberate malfeasance, do. So that happens to be an important step in the removal process. Unfortunately, once again, we are running a bit low on time. So what I'm going to do is I'm going to end it here, and in the next episode, we're going to finish looking up at the implementation of the linked list. In particular, looking up at the delete, how we're generating a random list, how we end up splitting that list later on so as that we can end up doing merge sort, how we output the list, as well as then this pop function, which is fairly useful, and we'll get into why it's named what it is and how it's in general used. So, thank you very much for watching. I hope you have a wonderful day.